Module 1, Section 3, Lecture 2. We're going to continue our discussion on electrophysiology, and in this particular lecture, we're going to define several important key terms. So our objectives: define the following terms that you see: resting membrane potential, action potential, synctium, polarized state, permeability, depolarization, repolarization, among some others that we'll bring up. And then we're also going to describe the ion shift that occurs during the cell's action potential, which we've already discussed briefly. So some important terms here. Threshold. The cardiac threshold action potential is the voltage at which a cardiac action potential is triggered in a cardiac myocyte. The threshold is usually around -70 millivolts. The cardiac action potential is a process that occurs in a ventricular muscle cell. The resting membrane potential of a cardiac myocyte is dominated by the potassium equilibrium potential. When the resting potential shifts towards a more positive value, the cell's voltage-gated sodium channels open, so sodium will start rushing in. Once they hit this threshold, then they will hit what's called an all or none phenomenon, meaning that once the threshold potential is reached, the action potential is inevitable and the cell is going to have an action potential or a electrical stimulus that's going to go to the myocardial cells. The cardiac action potential is essential for stimulating and maintaining the heart's regular contractions. So resting membrane potential is the state of a cardiac cell in which the inside of the cell membrane is negative compared to the outside of the cell membrane. It exists when cardiac cells are in the resting state. Action potential is a change in polarity, so it is when the cell becomes depolarized. So resting membrane potential is during the polarized state. Action potential is during the depolarization state. So action potential is a change in polarity, a five-phase cycle that produces changes in the cell membrane's electrical charge caused by stimulation in myocardial cells, which extends across the myocardium, propagated in an all or none fashion, which we just mentioned. Synctium. A synctium is cardiac muscle cell groups that are connected together and function collectively as a unit. So if you remember from anatomy and physiology, the atria have to contract together and the ventricles have to contract together. So all of the electrical cells and all the myocardial cells have to function in a synctium in order for this to happen at the exact same time. If it doesn't happen in a synctium, or if it doesn't happen in sync, then you start having some issues. Polarized state is a resting state of the cardiac cell, wherein the inside of the cell is electrically negative relative to the outside of the cell. So the inside of the cell is polarized, so potassium is full on the inside of the cell, sodium is on the outside of the cell. The cell membrane is in its resting membrane potential. And permeability, the ability of the cell membrane to change to allow the movement of ions. Depolarization, electrical occurrence normally expected to result in myocardial contraction, involves the movement of ions across cardiac cell membranes, resulting in positive polarity inside the cell membrane. So during the act of depolarization, sodium ions rush into the cell, changing the interior charge to positive after the cell is stimulated or after the cell reaches its threshold. And then repolarization is a process whereby the depolarized cell is polarized and positive charges are again on the outside and negative charges on the inside of the cell, a return to the resting state. So at this point, sodium's moving out of the cell, potassium's back inside of the cell, sodium ions returns to the outside, potassium returns to the inside, so the inside of the cell relative to the outside of the cell is more negatively charged. So, examining depolarization a little further. So during depolarization, this is the mechanical pumping action of the heart. Depolarization is the electrical aspect of the cardiac mechanical contraction. The action can occur only in response to an electrical stimulus. The impulse causes the heart to beat because of a series of complex chemical changes within the myocardial cells, i.e., ion movement or ion distribution between the inside and the outside of the cell. Depolarization, like we just mentioned, is the process of discharging resting cardiac muscle fibers by means of an electrical impulse that stimulates contraction. The myocardial cells are bathed in electrical solution, so they respond when there is a movement of these electrolytes. The chemical pumps inside the cell maintain the concentration of ions, which creates an electrical gradient across the cell membrane. And a polarized cell normally has a net internal charge of -70 to -90 millivolts. Now remember, again, the polarized state of the cell is when potassium is on the inside and sodium is on the outside, and there is a charge of -70 millivolts on the inside and a charge of 0 millivolts on the outside. This is resting.
That's right.
Or polarized. So when the cell receives a stimulus from conduction, the myocardial wall, or the permeable cell wall of the myocardial tissue, changes. The sodium pumps turn on, the fast sodium channels turn on, and it allows sodium to rush into the cell. Now, during this process, calcium will also enter, and then depolarization spreads, causing a mechanical contraction. So just a quick reminder of the ionic view or the ionic shift. So during the polarized or the resting potential, potassium is on the inside of the cell, sodium's on the outside. During depolarization, sodium starts to rush in way quicker than potassium comes out, but there is a movement of ions. And then during repolarization or the recovery state, sodium moves out of the cell and potassium comes back in, and towards the end of this stage, the sodium-potassium pump kicks on, and it brings the rest of the potassium into the cell, and it pushes the rest of the sodium outside of the cell. So again, remember, repetition leads to remembrance. Resting membrane potential is the state of the cardiac cell where the inside is negative and the outside is positive. And during action potential, you have a change in dipoles. You have depolarization. Dipoles change. The change in polarity produces a change in the cells. The inside of the cell becomes more positively charged because sodium has rushed into the cell and potassium has moved out. The electrical charge is caused by the stimulation of myocardial cells. So, as a quick review, the action potential at any point on the cell membrane acts as a stimulant adjacent regions of the cell membrane. So once the cell membrane starts to create an action potential, the whole cell membrane is going to receive that stimulus and it's all going to contract. Stimulus that is strong enough to cause the cell to reach that threshold and depolarize spreads quickly from one cell to another. And in the next lecture, we're going to talk about the cardiac action potential and how it is divided into 5 phases. And this concludes Module 1-3, Lecture 2. Be sure to study these key terms right here because they're going to be important. You will see them again.